so in this video, I'm going to cover a series of situations where we have one reactant reacting to form a product. And we're going to look at three different cases where the reaction in these instances would be zero order reactions, first order reactions, or second order reactions. So I'm going to start in order with a zero order reaction. So as I said before, the assumption is that in this reaction, we have only one reactant and it's going to form a product or more than one product, right? So first thing we can write down as far as the rate equation is concerned is that the rate is equal to minus the change in concentration of A over the change in time. As we said before, because a reactant is being used up, that's why we need the negative sign right here, all right? So therefore, when we write down the rate law, we can write it down as rate is equal to K times the concentration of A raised to the power zero, because remember we said that it's a zero order reaction. And of course, we all know from our previous math experience that anything raised to the power zero is going to be equal to one. So therefore, this simplifies to the rate is equal to the rate constant. So what that tells you basically is that the rate does not change. As long as the temperature remains the same, the rate will remain constant for a zero order reaction. Now we can rearrange this to get K is equal to rate over A raised to the zero. And if you look at it in terms of the units of the rate constant therefore would be the concentration over something. So it could be M over second, it could be M over hours, minutes, whatever, all right, depending of course on how fast the reaction goes. Now, I'm skipping, well, let me just say this. So therefore, since the rate is equal to this and the rate is equal to this, which is equal to that, we can simply equate these two terms together to get this, all right? Now, what I'm doing here is skipping some steps because to get from here to this equation, you'd have to have some understanding of calculus. I don't think that most of you in this course would have done any calculus, so therefore it would not make any sense for me to explain how we get from this equation here to this equation, all right? So this is just something that you have to accept as fact until you have some calculus experience, and then you can come back to it and see where it makes sense. So in any case, this equation relates the concentration of A at any time to time, right? So basically, you can use this equation to make certain predictions about how much of a particular reactant will be present at a particular time, or how long does it take for the concentration of the reactant reaches a certain level. So just to let you know what each of these terms represent, this represents the concentration of A at any time, as I said before. A0, A sub zero I should say, is the concentration of the reactant initially at time equals zero. K is of course the rate constant, and T is the time, of course, that can be expressed in different units, all right? Now, there's a concept, well, before I get to that concept, so based on this expression right here, one can plot a graph, right, which would be more useful when it comes to identifying or solving K. Basically, if you look at this equation carefully, let me get my writing function going. If you look at this equation carefully, and again, this is based on your math experience, you'll see that this equation is of the form y is equal to c minus mx, which is an equation of a straight line with a negative slope, all right? So the k would be the slope, x would be the t, and the y would be the a, and the initial concentration of A would be at the intercept, the y-intercept. And therefore, the plot is going to look something like, going back to my pointer, this, right? The plot is going to look like this, where when you plot the A concentration versus T, then you'll get a line with a negative slope, where the slope is going to be equal to minus K, and where the line cuts the y-axis at the initial concentration of A. All right, now at this juncture, I want to introduce to you the concept of half-life, right? it's an important concept which applies to a lot of situations, including dealing with reaction rates. And later on, you're going to see that the whole half-life concept applies also to radioactivity and also applies to biological systems, right? So it's something that applies to a whole lot of situations. So by definition, the half-life, which is represented by T half, is the time required for the concentration of the reactant to decrease to half its initial concentration. So in other words, when the time is equal to the half-life, the concentration of A would be equal to half the initial concentration of A, right? And it turns out that if you plug this value and this value into this equation, you're going to get T half is equal to the concentration of A initially divided by 2 times the rate constant. I could show you this. In fact, let me see if I can squeeze it in up here. I hope I have enough space for this. Okay, so let me try to squeeze it in this space right here. So if I plug in for A, if I plug in concentration of A over A0 over 2, and that is equal to the concentration of A0 minus KT, then basically this will simplify to KT equals to the concentration of A0 minus concentration of A0 over 2, which works out to be concentration of A0 over 2, which means that, oh, by the way, T would be half-life here, so this would be T half. So this should be T half here, right? So therefore, T half would be equal to concentration of A0 over 2K, which is the same thing as this equation down here, all right? So I just thought it's important that you, let me just put this in a box so that you can see that this is a separate thing. Okay. Okay, so that basically shows you how we derive the equation for the half-life of a zero order reaction. Okay, so that's basically all that there is to discuss about zero order reactions. And I think I might, after this video, post another video showing you some examples, how to apply these equations and so on. So let's move on now to the first order reaction. So in the case of the first order reaction, again, we're assuming that there's only one reactant forming product or products. And basically the rate of the reaction would be equal to K, let me go back to my pointer here, K times A raised to the 1, right? So that basically is the equation for a first order reaction. So we can rearrange this to get rate is equal to, K is equal to rate divided by A. And in terms of the units, you'll see here that in this case, the units of rate is M over S. As I said before, the S could be replaced by hours, minutes, whatever, depending on the unit of time that you choose to use. But in this case, we're using M over S, and that will be divided by A, and the M's will cancel out. So you're going to end up with the unit of the first order reaction constant being 1 over S, or S to the minus 1. Again, if you're using other units, it would be hours to the minus 1, it would be day to the minus 1, year to the minus 1, all depends on the nature or how fast the reaction proceeds. So therefore, we can set up this relationship where this term is equal to this term, and we can, let me just click on this here. And again, unfortunately, I have to make a jump in terms of showing you that the actual equation that relates the concentration to time derived from this equation will be this. Again, you're going to need some algebra. I'm sorry, not algebra. You're going to need some calculus in order to be able to derive this equation here from this equation, right? So again, this is just something that you have to accept for now until you have some calculus experience. Okay, so some definition of terms. It's the same thing as before. this is the concentration of A at any time t, and A0 is the concentration of A at time equals 0. And in this particular case, if you plot concentration of A versus T, you're going to get a smooth curve. Again, this should be something that you should know from your algebra experience. That would be basically the shape of a curve which has this general equation of, let me go to my pen function again, y is equal to some constant, doesn't matter what the constant is, let's say c times e to the minus x, all right? So basically that would be the shape, general shape of that kind of curve, all right? So another plot, which is more useful in terms of determining the rate constant, is if you plot the natural log of A versus time. Now, let me explain what's happening here. Again, this should be something that you should be able to understand based on your previous algebra experience. So what I'm going to do here is show you how to get from here to here. So the initial equation is A is equal to, concentration of A, I should say, is equal to the initial concentration of A times e to the minus kt. And therefore, we can rearrange this to get concentration of A times, divided by, I'm sorry, concentration of A0 equals e to the minus kt. And then we find a natural log of both sides. So natural log of this side would be equal to the concentration of A divided by concentration of A0. And that is going to be equal to minus kt, all right? And therefore, we can also rewrite this as ln concentration of A minus ln concentration of A0 equals to minus kt, which can be rearranged to get ln A equals to minus kt plus ln concentration of A initially, right? So in actual fact, there are several forms of this equation that you can find useful, and it depends on the problem that you're trying to solve, all right? You can use this form. You can use this form. I think these are the two main ways that this expression can be used. Typically, you would use this form of the equation if you want, well, actually, you would use this form of the equation if you want to find the concentration of A, right? Or you could use this form if you want to find the rate constant. And this form also, as I said before, I think I said before, when you plot ln A versus t, right, you get a straight line where the slope is equal to minus k and the intercept on the y-axis is equal to ln A initial, all right? So that's basically what happens in the case of a first order reaction. All right, and again, I'm going to give some examples in the next video so that you can get a feel for how we can use these equations to solve problems involving first order reactions. Okay, so, whoops, I pressed the wrong button. Okay, this is just rehashing what we said before, the half-life. Now, we're going to apply this to the first order reaction, but just to remind you what the half-life is. It is the time taken for the concentration of the reactant to decrease to half its initial concentration. All right, so when T is equal to the half-life, therefore, based on that definition, the concentration of A at that time is equal to half the initial concentration. So if we plug in to the equation that we showed you before, the values of T half, or the expression for T half, and A0 over 2, this is what you're going to get, right? And this is going to simplify because the initial A's will cancel out, and you're going to end up with the half-life is equal to ln 2 over k, all right? So that's the half-life expression for a first order reaction. And if you plug ln 2 into your equation, into your calculator, I should say, you're going to get 0.693. So sometimes you'll see in some textbooks, they just put 0.693 divided by k. It's the same thing, all right? Now, one important thing I want to mention before we move on to this example, and it is this. You'll notice in the half-life expression for the first order reaction, there are no concentration terms. So what that tells you is that the half-life for first order reaction is independent of the initial concentration of the reactant, right? And that is very different from what happens in the case of the zero order reaction. Let me just scroll back a bit so that I can show you what's happening in the zero order. If you look at the half-life expression for the zero order reaction right here, you see that there's a concentration term. So what this tells you is that the half-life for a zero order reaction is dependent on the initial concentration of the reactant. So that's what happens in the zero order reaction. That is not the case in a first order reaction. The half-life is independent of how much of the reactant that you started off with initially. All right. Okay. So let's apply what we have just learned to this particular question. It says, what is the half-life of N2O5 if it decomposes at a rate of 5.7 times 10 to the minus 4 seconds to the minus 1? All right. So in this particular case, it gives you the rate constant, not the rate, but the rate constant. Okay. I neglected to read that carefully. So basically, it's the strict application, direct application of this relationship right here. The half-life is equal to ln2 over k. So basically, all we have to do is plug in the numbers. Half-life is equal to ln2 over 5.7 times 10 to the minus 4 s to the minus 1. So let me do that here. 2 natural log divided by 5.7 times 10 to the minus 4. And the answer I got when rounded out to 2 sig figs is equal to 1.2 times 10 to the 3. So I'm going to put here 1.2 times 10 to the 3. And the units here would be seconds, right? Because we have 1 over s to the minus 1. So this would be the final answer. So that's basically how we solve that problem for first order reaction. All right. One thing I should point out too, and these are some of the tricks that can be involved when it comes to answering questions. One may ask, how did I know that this question relates to a first order reaction? And the answer has to do with the units, second to the minus 1, right? Because the units is second to the minus 1, I knew immediately it was a first order, a first order reaction. And that is what we stated in the previous slide. Let me come back to here. The rate constant units is s to the minus 1 or 1 over s. So I knew immediately it was a first order reaction. And as I said before, other units of time can be applicable as well. So the units could be hours to the minus 1, minutes to the minus 1, years to the minus 1. It doesn't matter. As long as it's a unit of time raised to the minus 1, then I knew that it was going to be a first order reaction. Okay. So the actual problem is solved here as well. I forgot about that. Okay. But that's basically it. All right. And this is basically answering the question a question to which I already answered, right? The units of k is second to the minus 1, and that's how I knew that the reaction is first order. All right. So this is basically a plot of the natural log of N2O5 versus time for the reaction that we were just discussing in the question previously. And you see, as suggested by the previous slide, or the previous 2 slides, I'm sorry to be going back and forth. Remember I said that when you plot, let me go back to my pointer function here. When you plot ln A versus time, you're going to get a negative slope line where the slope is equal to minus the rate constant and the intercept is equal to the natural log of A initial. And that is what is being demonstrated in a real example here in the case of the reaction of dinitrogen pentoxide reacting to form nitrogen dioxide and oxygen. When you plot the natural log of N2O5 versus time, you get a line with a negative slope, and you can use the slope to determine the rate constant, and the intercept on the y-axis is equal to natural log of the initial concentration of the N2O5. Okay, let's look at this reaction. Reaction A to B is first order in A with a rate constant of 2.8 times 10 to the minus 2. How long will it take for A to decrease from 0.88 m to 0.14 m? Okay, so in this particular case, let me go to my pen function. So in this particular case, first thing I'll write down is the relationship between the concentration of A equals to the concentration of A initial. In fact, let me see here. Let me see here. Let me see here. Let me write a different form of the equation. I would use this form. Ln A over A0 you know what? Let me go back to the previous form. I'm sorry about this. Ln A initial, or not initial, Ln A is equal to Ln A initial minus KT, all right? This is the form of the equation I would use because using this form makes it easier to solve for T, which is what the question is asking for. So the question is asking for T. Now, what has the question given us? The question gave us the initial concentration of A. The question gave us the concentration of A at the time. The question gave us the rate constant. So basically, the question gave us this, and this, all right? So all we have to do is solve for T. So basically, T would be equal to ln concentration of A minus ln concentration of A initial over minus K. And we can actually simplify this further to get ln concentration of A divided by concentration of A initial over minus KT. All right, so this would be equal to ln concentration of A, which is 0.14 m divided by 0.88 m divided by minus K, which is 2.8 times 10 to the minus 2, s to the minus 1, whoops, minus 1. And of course, there should be a minus sign here, times T. Oh, actually, T is what we're trying to find. Sorry. So all we have to do is put the numbers in. 0.14 divided by 0.88 equal, then find the natural log of that, divided by 2.8 times 10 to the minus 2. And according to my calculation, this works out to be equal to 66 seconds. So, and that's basically how that is done, all right? Okay, so that's how that one is done. Okay, let me skip all this here because this is just basically what I just did. So let me skip all this here. Okay, so in the case of a first order reaction, this is what happens when you plot the concentration versus time. You get this smooth curve, and one can go back to the pointer again. One can see, so that's a smooth curve right here, and one can see how the half-life can be discovered, determined, and you'll see that the half-life is constant, right? So you're starting from A initial to half the amount. The half-life is this value here, right? Which is 1 minute according to this scale down here. And then the half-life decreases again, right? For another minute, right? The concentration goes down, so the half-life is constant for another minute. Another minute passes, same thing. Another minute passes, same thing. And it basically continues until well, it approaches the x-axis, but it does not touch it, basically. So one can see that there's a relationship between the half-life and the concentration based on this expression here. The number of half-lives results in the concentration of A equal to the initial concentration divided by 2 or 4 after 2 half-lives, or 8, and so on and so forth. So you can see basically the progression in terms of the concentration falling, but the half-life remains the same. All right. Okay, I'm going to stop here because I need some time to recover. Because I want to talk about second order reactions next. So that's it for now.